Well, today is another beautiful day that I want to explain TransferNet article and also Subgraph retrieval enhanced model. But before that, I want to review another article, which is an interpretable reasoning network for multi-relation question answering. It's a very simple model. We calculate the probability given your question and states. So here we have states. For example, we have in this state and we go to another state. It seems very interpretable, but you have to make lots of projections in order to make it work. So, for example, we have M that is relation to question map. So lots of maps. We have relation to state map. So but these are parameters. It should learn that. So it is costly. But we can solve it pretty easier with other approaches. Still, even in this conjunctive questions, it cannot do well. It does not scale well. So we should talk about a beautiful article called TransferNet. And it supports both label and text relations in a unified framework. I think I have explained TransferNet before, but I want to explain it again because it's a really important article. So the question is, what organization did the wife of Bill Gates found? This question has some entities. So you see, at each step, it attends to different parts of the question. So it computes activated scores for relations and then transfer the previous entity scores. So not only we are calculating scores for entities, but also we are calculating scores for relations. And the generality is that it can deal with label form, text form, and their combination. Effectiveness, the TransferNet outperforms previous models, achieving 100% accuracy. It's not strange because 2-hop and 3-hop and these things are very easy on meta QA datasets especially. Transparency, TransferNet is fully attention-based. It's a kind of self-attention like transformer network that you have keys. So it's some kind of self-attention. So its intermediate steps can be visualized. And the core idea is that we have relation scores. So given a question at time t, because these are steps, and so we have relation. We have different relation at different time. So this is an example. For example, you go from this entity to another entity with some probability. This is the probability of relation. These are the probabilities of a relation. So these are different paths, like the path or trajectories of reinforcement learning. So these are some paths, but we are not using any reward or anything like that. Of course, you can interpret it like that, but it's much simpler. Starts from topic entity, then we maintain an entity score vector, probability of an entity being scored, being activated. So, and after that, we attend to some question war, compute score for relations. That W, as I told you. Then formulate these relation scores into adjacent matrix. For example, what is the probability that I'm in this entity and then going to another entity? And here we calculate, so if you want to jump along any direction, I just need to multiply the entity score and relation score. That's it. Then I have everything. Then I can arrive at target entity after repeating for multiple steps, multiple jumps, because it's multi-hop reasoning, and we arrive at the solution. A solution is a good way to backpropagate and tune the parameters of the neural network. So this is very beautiful. You have an encoder, just usual. You can use recurrent neural networks, LSTM, BiGRE, anything you like. But here, because there is no other sequence, there's just one sequence of question, there is no other sequence, so you should do some kind of self-attention. So that's why we create this. It's a key, attention key, because when you want to calculate these weights of your HI to create the context, these weights comes from the dot products of your attention. This is the dot product of your keys and your hidden representation. Because we have just one sequence, so we have hidden representation of a sequence, and we need another one. So that could be itself. So it's an attention key. It could be itself. So that's why we have the weights in order to create this beautiful context. And now that we have the context, we can use this context to calculate the relation scores. Because at the end of the day, these are relation scores that matters. Because we can jump across edges. It's just a simple independent probability rule that because this is independent of this, we can multiply them. That's why at time t, we arrive at A. And so the previous entity score is AT minus 1. The relation score is this. And now the current entity score is this. Because if we know the current entity score, we can use that current entity score to calculate, to create this loss. Because we know the target score. We know the gold answer. We know the gold answer at each time, and then this is the gold answer, this is what we have predicted, and so this is a good loss. So let's come back to what I was talking about. So and here, because the probability of relation if I'm going to I to J depends on many predicates, on to B, because we have B labels for each entity, so we marginalize like that. And here we use softmax here to create a probability out of that. And so the entity with maximum A star, maximum score A star, is the answer output. As simple as that. So this is the architecture, and so you see that it's a very interesting, easy framework. Here is that matrix that I told you, and these are the results. You see that in 3-hop, which we assume that it is much more difficult than 2-hop and even 1-hop, it got 62% accuracy, but TransferNet gets 100% because it's an easy model, because TransferNet is state-of-the-art models, I guess. I don't know if any better article for that, especially for this MetaQA. Of course, MetaQA is very easy, so we should compare it to other things. And there are other data sets, WebQSP, complex web questions, so that you get even lower things because it's more complex. You see even 52. But TransferNet gives 71, so it's a slightly improvement. And so I want to explain another article as well today, that is Subgraph retrieval enhanced, because sometimes you see that when you're doing TransferNet, you have to deal with big graph. But this article suggests that you just create a subgraph that is important to you. You don't need to deal with all of the graph. The real graphs are really big, and in any application, social media. So you just need to stick to very small subgraph. And that's why you can think about it as a You know, in open domain question answering, we usually tend to decouple reasoning from retrieving. Here we are doing the same idea. Here we are retrieving, we are searching for example, we are searching paragraph in open domain. Here we are searching for just subgraphs. We are searching for subgraphs. Which subgraph should I attend to? Should I focus? And then after you have found that subgraph, then it's easy. Then you move from retrieving to answering, and then so we multiply them. So you can think about it as a kind of. I always think about it like a Bayesian framework. In the Bayesian framework, for example, here you could think of this as a prior. So I will explain it. Prior and then likelihood and then posterior. So you can think about it like that. Because we don't know the prior. What is the prior subgraph that is good to go? So the pros, and you have pros and cons. Pros, a small subgraph is highly likely to exclude the answer. But a large one might introduce noises that affects the QA performance. It may exclude the answer. This is bad because because you are creating subgraph, a very small subgraph, maybe the answer is lying near the boundary, or you are missing out. You're missing that. And so, as I said, we can think about it as a retriever-reader system, and like any other algorithm that we do in open domain question answering. But it's not open domain here. We are just using that analogy. So so think about it as a metaphor. Because our minds works like metaphor. You know, everything that we learn, everything that a child, my niece is 4 years old, she understands everything with my metaphor, but the metaphor of a child. And so these are interesting ideas for cognitive linguists and also in cognitive science in general. So let's come back to our target distribution that I told you. This is a prior distribution that I told you. This is the reasoning part. And here, so we have the target distribution. The goal is find the parameters that maximize the likelihood. So the likelihood is this, but we want to know what are the parameters, because some parameters come from you finding your subgraph, that's theta, the parameter theta. Another parameter phi comes from the answering part. Because the reasoner and retriever are decoupled, we can train the retriever first and then train the reasoner. Just like what we do with, of course you can do it end to end, but you have two options. Probabilistic formulation of knowledge-based question answering. So we want to find the parameters that maximize the likelihood. So it's a beautiful decoupling. We can first train retriever. Why am I repeating these sentences? I told you. So the retriever needs to calculate p theta graph given your question for any graph which is intractable as the latent variable is combinatorial in nature. To avoid enumerating your graph, we propose to expand top K path relevant to your question from the topic entities and then introduce the subgraph following these paths. So these are expanding paths. And path expanding starts from a topic entity following a sequential decision process. So this is the probability of relation being expanded. This is an extra thing in this algorithm that, for example, n is your virtual relation. We don't have n, but just like in sequence-to-sequence model, you remember you always have a start token, end token. Here I have the same metaphor again, the same idea, the same analogy, let's say. And this is just the threshold of relevance score. So the probability of a relation is now, given your question, is now this. So this is the overall of subgraph retriever. Here we have the retriever part. These are retriever parts. But after that, we have the reasoner part. And the likelihood tries to match them, to connect the reasoner to retriever. So we do it through the likelihood. Because the likelihood gives something to posterior, and we have NK paths and trees. And finally, for reasoner, we need this likelihood. What is the probability of answer given your question in the graph? So we also use stop gradient operations, stop updating. This is a good technique. It's a trick, let's say. It's not really mathematical. You are ignoring many things, many things in mathematics. But it's a good thing. It works. And so this is end-to-end fine-tuning that you need to know. And this is the overall algorithm that you first pre-train the retriever, and then we sample subgraph, and we update the parameter phi and theta. Phi, we have two kinds of parameters, and that's it.